All right, sorry, I had to restart the recording. I guess like a club is in here, and then the person who was in charge of the club got very frustrated that I was in here. But I still have 5 minutes, so I'm just gonna quickly say again what I said. So here we have, it's a kind of a system with a bunch of capacitors in parallel and in series. We have to remember that a capacitor in series, we do that inverse addition, and when in parallel, we'll just add them up to find, the capacitors shared by them. Here, it's kind of initially complex, but our goal is just break it down to simpler and simpler diagrams until we can just find, what the equivalent capacitance is. Right off the bat, I can see that these two are in series. And how I know they're in series is there's no junction between them, right? So because there's no junction between them, we get to just do that inverse addition. As you can see here, I did C1 times C2 over C1 plus C2, and that's kind of a quick way to do that inverse addition, but it only applies when there's two variables, right? So if there's more than two variables, you'll have to just do, 1 over whatever plus 1 over whatever, etc. Okay, and then these two are both the same because it's C1 and C2. So that means we now have CS, which is that shared capacitance. So if we were to redraw our diagram, which I recommend that you always do, we'll see that we now have a system that looks something like this. Okay. And then that's to point B, right? So here's our CS, here's CS, this is C3, C2, C2. Okay, so now we have something in parallel, and how I know they're in parallel is the current has to go through a junction. So you can imagine the current of a river, just like the current that's going through this system, right? It's electrical current. Whenever there's a position where the current will diverge, so like imagine in the water, right? Like if there's like a fork in the stream, the current will go both ways. That is a junction. So we can identify that as a junction, and because of the junction, that tells us everything there is in parallel. So now we have C3, and both of these CS is in parallel. How do we treat a system in parallel? We just add them all up, right? So that's going to be 3.3 plus 3.3 plus 2. So that comes out to be 6.6, right? So I'll call that CP1, because these guys are also in parallel, but I don't want to get ahead of myself. So 0.66 microfarads. Okay. The next thing we're going to do, I'm kind of combining steps here because I don't want to delay the club or whatever, is these guys are in parallel too. And that's per the same logic, right? So there's a junction here. The current has two choices. It can go this way and down, or it can go this way and down. They're both in parallel. I'm going to call that CP2. So CP2 then is equal to C2 plus C2. So that's 20 microfarads. Okay. And then we're going to have to reorganize this diagram one more time. I'm going to draw it this way. And now we're going to have A going down into CP1 going down into CP2. And then, B, right? CP2. All right. And then they're in series. There's no junction between them. So we treat them parallel and parallel. And we treat them as they are in series. So again, a system in series, all we have to do is that inverse addition. When there's two, we can do the quick way. So we'll say the equivalent capacitance is equal to 8.66 times 20 over 8.66 plus 20. And then that whole thing actually comes out as 6.04 microfarads. And that's your answer. That's the equivalent capacitance of this whole system. I just want you to recognize that every single time you combine them, you redraw the diagram. So initially C1 and C2 are parallel, but as a combined system, C1 and C2 are in series initially, but as a combined system, they're now in parallel between all three of each other. I want to see that this question asks, it just asks for the equivalent capacitance. So that's what CEQ is equal to. All right, I'm going to wrap this up. Thanks for watching, guys.